Alright folks, we are back with a practicum after our spring break, and we are now working towards project 3. So today we're going to kind of combine two practicums into one video. So if we're looking at the project 3 instructions, we are going to cover importing data layers, and interpolation, and actually we're going to do a little bit of satellite imagery analysis. We're going to create an NDVI index map from some Landsat imagery. The first thing that you'll want to do is to download the project3.zip. This is going to contain the base data files that we need to import. So at this point what we're doing is we're going to still be working in Wadi Hassa. We're going to be working towards creating a predictive model for a set of archaeological sites from our original sites database, and we're going to add just a couple of external data inputs. So we're going to use that satellite imagery to create the vegetation index, and we are going to be working with some paleoclimate model output that is going to give us some estimation of what the temperature and or the precipitation was at various times in the past. So we will deal with that data, importing it and interpolating particularly that paleoclimate data to a proper resolution so that we can work with it in the predictive model that will be the culmination for project 3. So please download that and put it somewhere sensible on your computer and extract it. So for me, I downloaded it to my just general GIS projects. So I am going to extract it there. This is not a GRASS data set. These are just raw GIS files. So I mean, you could open them in QGIS directly to explore them first, but we are going to learn how to import these things into GRASS. And inside the project 3 directory that you'll get when you unzip that folder, you'll have two other directories. The trace 21K is the paleoclimate data, and there's a lot of them there for different time periods. We have AP, which is annual precipitation, and then MAT, which is mean annual temperature. So there are a lot of other climate variables you can download from the CHELSA website. I've given you a link to it over here in the project 3 document. And you know, these two here are reasonable ones to think about for predictive modeling, because precipitation and temperature might be relevant to why people chose to put their sites in the places that they are. And again, the final thing here, the 2 KYA means this is from 2,000 years ago, 5 KYA, 5,000, 8, 12, 15, and 22,000 years. I just chose these intervals because they are relevant to different time frames from the data sets in the Wadi Hassa survey data set. Obviously 2,000 years ago is the sort of Nabatean Roman time frame. 5,000 years ago is more like the Bronze Age. 8,000 we're talking about the Neolithic. 12,000 we're talking about like the Epipaleolithic and maybe the very early PPNA. 15,000 we're in that Mesolithic, Epipaleolithic, and 22,000 we're in the late Upper Paleolithic. So depending on which sites you chose, eventually you're going to want to choose a different time frame for these. But first, we're really going to deal with the Landsat data. This is again satellite imagery from NASA's Landsat project. These are relatively recent ones. Landsat 8 is one of the more recent missions. You can go all the way back again to the 1980s with Landsat MSS, but the resolution on those is quite a bit rougher. So these ones are going to be mostly in that 30-meter-ish resolution that matches already with our SRTM. And there's a whole bunch of files in there. These are all geotiffs. Each one of these mostly is one band of light from one of the sensors aboard that Landsat satellite. And in the document, I have given you a table here that breaks down the different bands, what wavelength of light that they are actually recording, what the horizontal resolution is. You can see that the panchromatic is actually red, green, and blue all together, so it's a black and white image, and it is the only one that's at higher resolution of 15 meters. So that's actually pretty good, but most of them, the individual red, green, and blue, for example, are at 30-meter resolution. And we particularly are going to be interested in the red and the near infrared, because these ones are really, really sensitive to vegetation, especially green growing vegetation reflects very brightly in these two areas, and we're going to use those to create our NDVI, Normalized Difference Vegetation Index. So you could follow along with the instructions here, but I will briefly show you how to get these data into grass. So here I am, I'm in my same location, and basically the permanent map set that we've been working in, the same grass location with all our Wadi Hassa data. The first thing that I want to do is to create a new map set inside that location, and I'm going to just call that Landsat, because that's what where we're going to import our base Landsat imagery. So we click OK. Once that is done, and here we have confirmed that we are in the Landsat map set. It says current. To import any grass or any GIS data, we go to the File menu, and we actually have a lot of different import options. Import raster, import vector, import 3D, import database. And then we have the also the export tools if we wanted to take data from the internal grass database and put it out into a standard shareable GIS file. We would use those. The import menu for the different types of GIS data, they have a variety of tools. Most of these are specialized. You would only use them if you, for example, knew you had a DXF file that you were trying to get in, or a LiDAR point cloud or something like that. Generally speaking, we would tend to use the top two, the sort of simplified or slightly more in-depth generalized import tool for vector types, or in our particular case here, for raster types. And the tools are actually external projects that are kind of built in with grass, and particularly for rasters we use GDAL, which is like Geodata Abstraction Layer, I think is the actual acronym. And same thing with vector data, that OGR is the external tool, and they can read multiple GIS formats, various types of raster and vector data formats. These will help you import them. And then on top of those, the grass team has built these sort of convenience modules, because in the past you wouldn't know what the CRS was, the coordinate reference system of your imported data necessarily. It wouldn't necessarily match, I would say, with the current location that you're working in. So you would have to create a new location to match that CRS, import that data, and then reproject it. And you can still work that way, but now the grass team has built in this automatic reprojection while you are importing your data. And this tends to work really well. However, there are times when you might have to get sort of a little bit more under the hood, and that's when you would go for the more detailed tool RNGDAL. But today we are just going to work with r.import, and again, it is a higher level module. A lot of the real detailed stuff has been abstracted. That just makes it a lot easier for you to work with. Basically, you have to decide, do you want to import an individual raster file, or do you want to import a whole directory of raster files? And for the Landsat data, you could totally do the directory. So I'll show you what that looks like. Eventually, I'm actually going to go with individual files, because we don't need all the bands of light for what we want to do, and they actually take up a lot of hard drive space. So unless you are really wanting to explore what all the different bands look like, we're going to focus on doing individual bands in a minute. But if I wanted to get the whole directory, I would click the button directory, I would click the format button, I'd scroll down to the container. In this case, it's GeoTIFF. So we have all these different raster formats, but we would scroll down in this particular case all the way down to GeoTIFF, and the extension, it's the dot whatever at the end of the file names, .tif or .tiff potentially. And then I would browse to where I unpack that. So for me, it's under my GIS projects, project 3, HASA Landsat. And you can either highlight it just like this, or you can actually double click into it, and you can see all of these there. And then GRASS will automatically find all the individual layers. And you can actually edit the output names, but by default it's going to keep it the same as the input names. So from this point, you could actually just uncheck the ones that you don't want and keep the ones that you do want. And that will work just fine. It will automatically do them all. But I want to show you how to import one layer at a time. So in this case, we'll click with the default just individual file. We will browse. We will go where our data lives, and we will find the bands that we actually want to import. So looking back here for our project 3 instructions, we are going to want to get the red band, the near infrared band, and while we're at it, we'll grab that panchromatic band with the higher resolution black and white imagery. So really what we are looking at is the band 5, band 4, and then the bigger band over here is going to be 6, 7, band 8. Okay, so let's get back into our RNG doll. Where is it? There in the background here. Okay, so let's do band 4 right here. Just click open, and we oops, I guess I was sort of in that from before. Let me just close that. I don't know why it was still up there again. Try that again real quick, okay? Simplified raster import with reprojection R import, individual file, GIS projects, project 3, Landsat, and then we're going to get band 4. And I recommend, let's just renaming this red, just so that you can keep it a little bit straight in your head. And then hit enter, and then you should be good. So we just want to check all this stuff, and we can hit import, and it should go ahead and do that for us. Now again, this is a convenience module. It's going to import the whole band, or the whole tile, which covers a lot more than what we want. If we wanted to, we could click on import settings, and we could actually clip it to the region. So let me do that. I'm also going to put this okay, let's just see. Oh, here it is. Allow output files to overwrite. So I'm just going to overwrite this again, and I'll hit import, and when it does it the second time, eventually it will clip it just to the region that we are working in. So if we set our region to match the SRTM, which it probably should be at this point, we can do that in multiple ways, but the simplest way is to right click it, display the layer, and then right click it down in the layer manager, and then set computational region to match that map. So obviously do that ahead of time. And then if you want to not have the entire, big Landsat tile and just sort of save some space for you in your GRASS, you can do exactly what I did. Under import settings, optional, output raster map extent set to region. And the resampling method is set to nearest for imagery data. That's correct. For other data, when we do the next, I'll talk about the other options that we have over here. And the resolution is going to be estimated from the input set, so we don't have to mess with that as well. Okay, so we've done red, let's now get our infrared. So we're going to get band 5, and I'm going to just call this one Landsat NIR near infrared. Hit enter. And again, we're going to leave everything the way it is. We're going to clip it to the area. We will hit import. We're going to do that. And then once that is done, we are going to now browse for our band. I guess I didn't include when I downloaded the when I downloaded the Landsat, I didn't get the high resolution band. So we'll just forget about that for now. Okay. So we'll just cancel that, and we'll come back to this interface again when we're going to import the Chelsea climate data in a little bit, but for now we can hit close. So here we are in our Landsat directory, and we have, I'm just going to remove my duplicate layer here. We have our red and near infrared imagery. So if I flash back and forth between them, we actually can get, we can see that the intensities are different. Now, if we were going to spend a lot of time on satellite imagery, I would show you how to calibrate some of this imagery. I would show you how to make a false color image, but really all we want to do at this particular point is to do a vegetation index. It's really cool to see the images, and it'd be nice to maybe make a RGB image, but we don't really need to worry about that at this particular moment. All we're interested in is getting an additional index layer of vegetation health, potentially to input into our predictive model that we are going to do next week. So I'm going to introduce you briefly to the imagery tool set over here. There are a lot of really cool things that we can work with over here, including making those false color images, classifying images, pan sharpening, a lot of things I talked about in the lecture before spring break. But really all we need to do at this particular moment is to go down to where it says Satellite Images Products and go to the Vegetation Indices I.VI module. And here there are multiple indices that we can calculate. You can actually see there's a lot of indices. If this was a class on satellite imagery processing, we'd go in depth into some of these other ones. But we're going to stick with NDVI. It may not be the best or the most relevant to all research aspects, but it's certainly the most well-known and well-understood one. And to calculate it, you could, in theory, do some raster map, because basically it is the near infrared and the red, and you basically calculate it with this fairly simple equation where it's near infrared plus red, or red plus near infrared over near infrared minus red. So you could do that in the raster map calculator, but the IVI does this a little bit better for us. So we're just going to call the output of this NDVI. We're going to leave the vegetation index to NDVI. The inputs, we need to tell it the right imagery map. So we're going to pick red for where it asks for the red, and we're going to pick NIR, or near infrared, when it asks for near infrared. And this particular index doesn't need any of these other channels, so we don't need to put anything into those. We really don't need to worry about any of the other settings. We can just hit run at this particular moment, and when it finishes, we will get the NDVI map, and it will already be set to the NDVI color scheme using our colors behind the scene. And to show us what those colors actually mean, let's put the the scale on, and I always like to do that real quick, and I'm just going to move it over here like so. So the NDVI is an index that stretches between a maximum of 1 and a minimum of -1. Anything that is below 0 is probably going to be something like water, or potentially like blacktop, or other generally human-made stuff, although some natural phenomena might reflect in that way as well. So everything above 0 and below 1 is going to reflect the health of vegetation. Being a desert, you would expect to have a lot of fairly low values, and that is really what we see. But we can absolutely see some values in this color scheme. They're going to look green, that are relatively high. Now in Wadi Hassa, 0.51 appears to be the max, but that is going to be things that are very green or close to this 0.51 are going to probably be irrigated crops. So if we zoom kind of into this area here, we can really see it's irrigated crops or riparian wetland vegetation occurring down in the wadi itself. And that is really kind of an interesting thing for us, particularly if we are looking at naturally occurring places where water might accumulate, where there might be vegetation health, where it's possible to do farming now. It also probably was possible to do farming in the deep ancient past. Now, I will say that we have to be careful using modern vegetation data when we're trying to predict things in the past, because, for example, way out here, I know that a lot of this is due to deep well pumping of an ancient aquifer. So it may not have been possible to do farming in this level of intensity, but certainly these are areas where seasonally you might have been able to plant the wheat field and have seasonal rains potentially give enough moisture to grow a single crop. So we do have to be a little bit careful with using modern data to use in the past, but there are reasonable ways to go about doing this. Okay, so we've done our NDVI. Let's now work with importing and interpolating our climate data to a finer scale. So what I'm going to do is to create yet another new map set, and I'm just going to call this Trace 21K because that is the paleoclimate model that we are going to be. Oh, I already have a Trace 21K in this particular map set because I've actually imported a bunch of them already. Just to show you, I'm going to make a new one, and I'm going to call it Trace 21K underscore 2. You will not have to put the underscore 2 when you make yours, okay? And we'll let ourselves get into that new map set. And at this particular moment, I am going to remove our Landsat stuff for now because we're kind of refocusing on the next part of the project. And I'll just go ahead and remove the legend from the NDVI. Okay, here I have our new empty map set, Trace 21K, for me, Trace 21K2. And it looks like I actually have multiple ones here. I use these map sets for a lot of things. Anyway, we are going to get back into our import raster data, simplified raster import with reprojection. And here at this particular moment, we could again do our whole directory and go down to GeoTIFF and then browse over here to project 3, Trace 21K. We can click into it or we can just highlight it, and it should indeed find everything, but maybe let me just look at it really quickly. Oh, none of these things have extensions, so I'll just turn that off and see what happens. So in this particular case, because they don't have file extensions, they don't show up when we do the directory, but we can still get them with our individual files. So let's go back to GIS projects, project 3, Trace 21K. And here's where you have to choose. So depending on which set of sites you have been working with, and if you want to keep working with them for your predictive model, you need to pick an appropriate time frame. So we've been working with in the videos I've been working with the Nabatean towers, so I'm going to pick the 2 KYA climate models to work with. If you're working with older sites like Bronze Age villages, you're going to want to pick the 5000, or Neolithic lithic scatters, you would pick the 8 KYA or maybe the 12 KYA. And if you're looking at Paleolithic sites, you'd pick maybe the 22 KYA one. Okay, so I'm going to start first by importing the annual precipitation, and here we have that. I'm going to leave the name the same because it already kind of tells me everything I need to know. And in terms of the import settings, I am going to opt to clip it to the region, just again because I don't need extraneous data. Now these climate data are really coarse. They come at a 1 kilometer resolution. So we're going to leave these this estimated, but instead of nearest, we're going to pick by cubic or Lanxos. In this case, it won't make much of a difference. Lanxos is probably the most complex one, but nearest neighbor is great for things like imagery where the individual pixels, the colors of them might be discrete and there may not be a continuous pattern, across space. But anything that is continuous, like elevation data or climatology data or something like that, we'll want to pick at least something bilinear, bicubic, or Lanxos, because those are a more smoother, actually, interpolation when they are reprojecting this stuff. So I'm going to pick Lanxos. I'm going to leave everything else the same over here, and we're going to import that and let it reproject if it needs to. And once it does, we will see what it looks like. Okay. Did it do it? Okay, it did it, and it's showing me in white. Let me just quickly look at the metadata here and see what we've got. Yeah, we've got information in here. It's just that the color scheme is showing it in white. So let me put that over here and just apply a color scheme to this so that we can see what it looks like. I'm just going to pick Viridis and see if it will make me able to see any of the patterns. There we go. There they are. And again, these are 1 kilometer squares, more or less, that we see over here. And unfortunately, it did import it at a resolution of 30. So what I should have done was, instead of putting estimated, click on it and choose value, and then put 1,000 meters, and then I'm going to do the allow output files to overwrite, and I'm going to import it again. And it'll do it. Again, we're probably going to have to set the colors. I'll just pick again our Viridis scheme, hit run. There we go. Now we are looking better. Let me just double check the metadata to ensure. No, it still did it at 30 meters. So our import is not actually doing what I want. This may happen to you. It should be obeying this, but every once in a while it doesn't do that. So what I am going to actually do is to set that region resolution manually. So I went to settings, computational region, and then set region g.region, and I can close that one. Where is it? I can close that one, and there's my G region over here. And here I'm going to go to the resolution tab, the 2D grid resolution. I'm going to set it to 1,000, and I'm going to hit run. And that should have done it. Let's just confirm it by doing computational settings, computational region, show current region. And over here, yeah, it's showing me pretty much 1,000 like I asked it. And so now, let me import that again. See what it does. Okay. So I'm going to remove the extra layers over here. Set our colors just so we can actually see it. Okay. And now let's see what it has done with the metadata. Give me a second. I'm going to pause this because this should not be doing it this way, and it probably has to do with the way that I exported the data from GRASS to begin with. So just give me 1 second. Okay, folks, I figured it out. I was trying to be too nice to you. I had shrunk the size of these raw Chelsea data files, and in doing so, I inadvertently set the base resolution to 30 meters. The original files I downloaded, you can see they're really big, like 400 megabytes. But what I'm going to have to do is to host these on a Google Drive as unzipped, and you're gonna download them individually. I will update the project 3 description to show you how to do that, and you'll just go and pick just the years that the year that you're interested in, the 2,000 year one or the 5,000 year one. And again, we have mean annual temperature, and we're going to have annual precipitation. So you'll only have to download 2 of these, but they are quite big, 400 megabytes here and 535 megabytes here, for example. But the good news is that now it all works as expected. And they have the .tiff file name, so you could use that filter as well. But when you download them, navigate to the ones that you download individually, not to the ones that are in the project3.zip. And in fact, I might just update that to have the Landsat images in their own zip, and you can download those independently. So again, I'm going to import the annual precipitation from 2,000 years ago, the output from that climate model there, and I, in the import settings, have used Lanczos, set the extent to region, so we're not going to get the whole, actually the whole world, the Chelsea data are for the whole world, and I set the resolution value and set it to 1,000, and I've already left the computational region at about 1,000 meters as well. And now we are going to be able to import that. And because this is for the whole world, it's in a lat long projection system, and it will do the reprojection for us when we import it. And you'll see all of this text come out over here, and once that goes in, there we go. We have our, and you'll notice that the bounds don't exactly match because that is happening in that reprojection as we go. Now let me quickly grab the mean annual temperature from the same 2,000 years ago and import that and reproject it as well. And we will have both of those in our directory here now to work with. Okay, so now we can close that, and we have our data here. And what we're going to do is we want to take this 1 kilometer resolution and we want to turn it into, through interpolation, we want to fill in the gaps between that coarse, the center of each pixel, and the neighboring pixels at a finer resolution of 30 meters. So we have the trend at that coarse resolution. We want to estimate what it might look like at a finer resolution. Again, interpolation is not creating data. It is a model of what the data patterns that are missing at this coarse resolution might actually have look like. So while we see this as continuous at the 1 kilometer resolution, at the 30 kilometer resolution, we actually just have one data point every 970 meters, right? 130 meter data point, and we want to fill in the rest of those 30 meter squares between each adjoining data point in this 1 kilometer resolution original data set. So the first thing I want to do, again, this is super important, is to set the region to match our coarser data set. Set computational region from selected maps. Okay, and you can set it from the AP or the MAT. They should match. But we're starting with MAT. So the next thing that we want to do is to actually sample all of the center points of all of these pixels, the 1 kilometer pixels. So we're going to go to raster, and we're going to go to generate random cells, and we're going to pick random cells and vector points r.random. We used this before when we were doing our total view shed, so you should be relatively familiar with this tool. And here we have our input raster map, MAT, and that is what we are going to work with. The output, we are actually going to pick every single pixel in that input map. So all we actually have to do here is put 100 and the % sign, and it will get all the pixels for us. And we want to have an output raster map, output vector map, and we will call this MAT. Oops, I have my cap locks on. MAT interpolation points. Okay, and we have a couple choices that we can make at this particular moment. We could click this generate vector points as 3D points. We probably should do that. We could also well, it should also bring in the value from that into the vector table, but let's just do these as good practice. We'll hit run, and oh, sorry, we need to set the random seed. Just hit 1 there, and then we will do it. And once this goes, we will see little points in the center of every single pixel. So we have now created a points vector map. We've taken the data from that coarse resolution 1000 meter resolution raster map and put them point right in the middle of every pixel with that value. And now we can interpolate the gaps between each of those particular points. So let's just explore our points file real quick. Let's see if it did create the attribute table, and it did. The value there is that MAT value. I checked to make it a 3D because I wasn't 100% sure. Sometimes it doesn't grab it in quite right, but this value is what we're going to use for the interpolation. So this value in the table is what we're going to use. So now what we have to do is to reset the region to 30 meters and to the extent of our HASA DEM. So I have it here in the background in my layer manager. I'm just going to right click, set computational region from that. And to double check, I always do recommend going to settings, computational region, show current region, and we confirm that we have a 30 meter resolution. Now we can go ahead with the interpolation. So we go to raster, and we go down to interpolate surfaces, and we have a variety of tools that we can choose from, but in this particular case, and in general, I tend to recommend these days v.surf.bspline, because I tend to get the best results from this with the least confusion. So on the required tab, we will pick our MAT interpolation points. Then under the settings, we will pick the attribute column value. So those are the numbers that we want to interpolate. The data values are the mean annual temperature in degrees Celsius. And then we have to tell it something about those values, how stiff to make the splines as they go out, and how close we want them to intersect the actual known data points. So we have a variety of things that we need to tell it to manipulate those. So the first one are the spline steps in the east-west and north-south direction. Initially, what we need to do at minimum is to tell it to look at the nearest neighboring points. And that would be the distance between one point and the other. And so if we go just in that sort of plus-shaped direction, it's 1,000 meters. But if we go in the diagonals, it's going to be more than that. So we would put in something like 1,500 meters, just so that we could cover all the neighbors in that neighborhood, 3x3 neighborhood around each one. So at minimum, we need to put 1,500 in here for it to be able to do the interpolation properly. If we increase this step even more, to like 3,000, we'll go out one more rung in that window, and we will change the math to manipulate the shape of the spline by giving it more neighbors to look at in each direction that it goes out. And that might be what we want to do if we want to have a less wavy or less detailed local interpolation. We want to think about the general surface trend in the greater neighborhood. We could increase this value. For now, we're going to leave it at 1,500. We are going to change the interpolation algorithm. We're going to use the bicubic one. Bilinear is just simpler, and it will go faster, but it may be not quite as detailed of a result. And then finally, the Tikhonov regularization parameter affecting smoothing. This is the number that we tell it how close we want it to be in terms of hitting right into each neighboring data point. Do we want our spline to go right through them, or do we want it to have a little bit of a fudge factor so that it can go overshoot or undershoot some of the neighbors? And this one, it always is useful to look at the manual, because even I forget, whether I need to make this smaller or larger. And here in the manual is an explanation of what it is. A larger value will produce a smoother interpolation, which means that it will let the splines bypass. It won't have to go exactly through the middle of each data point. And by default, it does give us a reasonable value to start with. So if I want it smoother, I would maybe step this up to 0.1 and go from there. But let's just leave it at 0.01 to start with. And then finally, the outputs, we want to do the output raster map. And we will put MAT2K 30M interp, just so we know what we're dealing with. And we don't really need to worry about these. I mean, eventually you can look at all of the rest of this, these options in the manual and see if you want to do that. But here I would definitely recommend giving it as much RAM as you can stand. Again, I'm on my fancy computer here, so I'm going to give it tons and tons and tons of RAM. You might only have 4,000 or something like that, but give it whatever your system can give, because interpolation can take definitely a long time. So I'm going to hit run, and this might be a time where you have to go off and have a coffee and come back a good while later. But in our particular case, it seems to have finished, and let's go ahead and bring this up to the forefront. And now we can see our interpolated map. Let's just click the metadata on it and see that it is indeed at a 30-meter resolution. And we can see it does look a little blurry, right? But the spatial patterning between where we started and what we got kind of matches, right? But we have definitely got some detail here. And again, this isn't strictly necessary in this particular case, but I'm using this as a way to show you how to do an interpolation. Now we'll do that again. You're going to want to do that again for your annual precipitation. Just follow along exactly the same. First, you set the region to match the annual precipitation. Then you go to computational region, show region, and you confirm that it matched. Then you are going to go to generate random cells, rRandom. You're going to make sure that AP2K or whatever time frame is selected. Give the random seed of 1. Then you're going to put 100% I don't think you need to check the 3D, but I always do just in case. And we're going to give it an output name of AP interpolation points. Hit run. Let's go ahead and close some of these other ones so that we don't get confused. There we go. So now we have our points. We are going to double check by looking at the attribute data. We've got values in there for millimeters of rainfall. That is what we want. Now we are going to go back to our 30-meter DEM and set the region to match that one. Once that is done, we will confirm. The region is now 30 meters. And we are going to go back into our interpolate services vsurf bspline. Actually, I have it up in the background somewhere. And we are going to make sure we are now choosing the AP interpolation points. And we can leave all of these things the same. Again, you can tune these, but for these particular data sets, the values I've given you here should be enough. And we are definitely going to make sure we pick the value. And we're going to change this to AP 2K 30 meter interp, and we're going to hit run. And again, depending on your computer, you may have to wait a little while for this to do it. And at this particular moment, we have completed our final interpolation of our two paleoclimate data sets, and we are going to stop the practicum for this week, and next week we will pick up with the predictive modeling itself.